We have a number of people willing to join us today. We're all trying to fit on camera. We're here for a conference called Twitter Math Camp. We usually start these with just an introduction. If you'd share with my students who you are and maybe what your context is for calculus.
Sure. My name is Jasmine Walker, and I teach high school calculus in Burlington, Vermont at a small independent high school, to pretty small classes of about 12 students typically. And this past year I used a text actually that's from another professor at your university called the Active Calculus curriculum, but I've used a lot of other things as well.
And my name is Jim Doherty. I also teach at a small high school. I've been teaching Calculus BC for the past 5 years, and this year I'm also adding a non-AP calculus course to my schedule. And the way we run our non-AP calculus classes, over the course of the year, we only concentrate on the differential calculus portion of the course. We don't talk about integrals in that class.
I'm David. I'm from Australia. I teach at the University of Adelaide, and I provide learning support for all the students, including people learning all levels of calculus. I spend most of my time talking about integrals.
That makes sense. They're the tricky bit.
I'm Edmund Harriss. I'm at the University of Arkansas. I actually like calculus a lot more when it gets a bit further than you have with the multidimensional stuff. I do research looking at surfaces and how the calculus of that works.
We talked a little bit, kind of thinking about the differential view of calculus and how that leads off into being able to think about manifolds. And we thought about implicit curves, kind of as a start to that kind of thinking. Yeah. All right, so we haven't focused necessarily on a particular topic, but these fine people are willing to talk anyway. And they know it's kind of end of course. So what were you interested in sharing?
I've been teaching calculus for a long time now, and one of the things that has really become an interest of mine is seeing not only that my students can, navigate the algebraic wilderness of the class, but that they can actually, put their words and put ideas, explain the ideas of what they're doing, rather than just know how to do what they're doing, actually know what it is they're doing. And it's one of the compliments that I really value in my Calculus BC class, which we teach as a second-year group of kids. So often they're going back over topics that they've already learned, and I'll hear kids say, oh, I knew how to do this, and now I know why. So that's something that's always been really important to me. And what I was talking with Professor Golden about earlier.
John, hopefully you're going to be John.
So I was talking about with John earlier, a topic that especially interests me about that in beginning calculus is the mean value theorem, where my students typically train themselves to recite a formula, but have an awfully hard time pointing at a picture or talking about anything in their life that actually represents an application or an evidence of the mean value theorem. So I tell them about the fact that in my old state of Florida, you could get a ticket without ever being targeted by the police. Because you get a punch or a scan when you enter the highway at a certain place, and you get a scan when you leave the highway at a certain place. And if you leave the highway faster than you should have, you can get ticketed for doing so.
Like automatically, they send you a ticket in the mail?
You can, yes.
Oh, wow.
Wow, that's fascinating.
That is fascinating.
Yeah.
When I learned the mean value theorem, my lecturer said it was like if he was, I don't know if this is appropriate for your age kids. In Australia,
let's give it a go.
Australia, the drinking
if there's
age,
bleeps, you'll understand.
In Australia, the drinking age is 18. He's at the bar and he's feeling a bit tipsy, and as long as he arrives home, no matter what swirly path he takes, he must have been facing the right way at least once. That's his application of the mean value theorem. And I remember it now, and I think it was a really useful one. It's technically Cauchy's mean value theorem, but close enough.
Well, since we're talking about the mean value theorem, I think the thing that feels the most interesting to me is knowing when you can and can't use the mean value theorem, because I think you can recite it easily and get really caught up in the idea of what's inclusive or exclusive and why that actually matters. So an activity that I really love doing is trying to find the bounds of when it works and doesn't work, and what that really looks like, and what happens when you kind of try to break the mean value theorem of having something be where the continuity and differentiability, like where the edges of those things actually are.
Well, and that can be also a nice continuity and discrete distinction there as well. And typically the way we try to trap kids in a calculus example is to have an asymptote hiding inside and ask them about a range over that.
Yep.
It sounds like yours is an even more subtle distinction of continuous behavior in life versus discrete behavior in life.
Or that thing where you've got a function that has a kink in it, and so the mean value theorem doesn't apply. It's definitely a continuous function. But
Exactly. So it's not differentiable, but it's still continuous.
Yeah. I talk to students all the time who struggle with all sorts of things, and I see very, very good students who do very well at everything else, who struggle to create the function necessary to use the mean value theorem or the intermediate value theorem in an argument. So it'll say, we've got a couple of functions, and one of them goes from 0 to 1, and the other one goes from 1 to 0, show that at some point they must meet, for example, which is an intermediate value theorem sort of thing. But that idea that the intermediate value theorem and the mean value theorem work on one function. They are theorems about a single function. So if you have a feeling that one of those theorems may apply in a situation, you're going to have to create a single function that captures the information that you have. And that's a really useful thing that my students have to help maintain their focus when they're solving the problem. Because they have to say, well, maybe I needed something that captures how far apart those functions are, so that meeting means they're on top of each other, so I'll create a new function, h, which is f minus g, and then I can argue about that function to get the information I need. So, yeah.
Oh, that's nice, because we started off that lesson with a kind of famous puzzle about the monk walking up the mountain and the monk coming down the mountain. I like that focus of, well, the theorem only talks about one function. We don't get the 2 days.
Yeah.
And this is a place where the geometry is really important in the calculus. You're taking something that is reasonably clear. If you're just sort of drawing a line, you can see that.
If you draw a bunch of secants, it's not a surprise that you can draw a corresponding tangent, right?
And so it's sort of natural from the visual side, and you've got this rigorous proof where you describe a curve rather than just by drawing it with a pencil explicitly by a function, and then this property holds. And it's, for example, like going down to the one function, you're making sure you have the information, the visual information you need in the right place.
And this is one of those examples where I feel frustrated as a teacher more than I did as a student. I kind of wish that my calculus textbooks never mentioned Rolle's theorem, for example, which, why give them a whole separate name and a whole separate formula to try to remember instead of just observe that this is one of the consequences of the mean value theorem?
That's a historical thing, I reckon.
Yeah.
So I love the story. My favourite part of Rolle's theorem is to...
Have I been saying it wrong forever?
No, it's French, right? So it's Rolle. But anyway, Rolle's theorem. Everyone calls it Rolle in Australia because we've never pronounced anything correctly. We call him... anyway.
Especially when you can add an E to the end.
Yeah, that's Australian, right? Rolly. Hey, Rolly. No, mate. So I like the story that Rolle's theorem is actually, when he wrote it, wasn't about all functions and was only about polynomials. And when he wrote it, it didn't involve derivatives because he didn't believe in them. That's one of my favourite stories.
Oh, I don't know that one.
Yeah, he had something similar. He called it a cascade, but it was something that you did with polynomials. It was pretty much a derivative, but not quite. And it was a formal thing. It was just a calculation you did that helped you do some things.
So does this fit into like when Lagrange wanted derivatives to be kind of almost
it was
terms
around
in the
that
Taylor series?
I mean, it was around the time when a lot of people were really upset that it all seemed to be working, but it didn't have that foundation.
Right.
I can't remember, but
I arguments about the ghosts of departed quantities and
yeah,
things like that.
I think that might even be a Rolle
Yeah.
quote, actually.
No, that's Berkeley.
That's Berkeley.
That's Berkeley.
Yeah. But yeah, he just didn't believe in them, and so and I think it's really cool that the theorem that has his name today, really interesting, is about derivatives.
But at least that's a theorem that's named for the right person, unlike L'Hopital's rule.
L'Hopital's rule isn't.
It's one of the Bernoullis discovered that, but he happened to be working for L'Hopital at the time, so
Huh.
L'Hopital's name got stamped on it.
I didn't know that.
It's
Yeah.
basically, I think, the only example I know of a sponsored mathematics
Yeah.
theorem.
This theorem is brought to you by.
I like that you say didn't believe in derivatives
Yeah.
because I don't think it's, if you asked a calculus student, like the concept of like, well, do you believe in derivatives?
Yeah.
Feels like just an odd thing to say. Like you might
Yeah.
ask someone now, if they believe in something else, or like, do you believe in the Earth being round, or do you believe in derivatives? It's just interesting to think about a time when there was a part of your identity that you didn't believe in derivatives.
Yeah.
That this was a meaningful debate to have, and
Right,
Yeah.
that like people would
and a
actually
principled
talk about
stand
this.
to have. you know.
Right.
A derivative denier.
Yeah, I mean, it sounds
Yeah.
a little bit like a climate denier or something, a derivative denier.
Yeah.
So I think this is going to be a question for the final assessment. Whether you believe in
Derivatives.
derivatives.
And then the question 2 is that regardless of whether you believe in derivatives or not,
Please calculate all of the following derivatives. Yeah.
All right. So thank you. That's lovely stuff. If you were going to give these guys a word of advice, a lot of them will be going on to Calc 2. Is there a mindset or an understanding you'd want them to think about kind of having before they move on?
I'd say that the understanding of what something means is very important, but also it's a completely separate type of learning from being able to figure out what to do today when someone asks you to do something. So if you're given an exam question or an assignment question, that choice of what am I going to do with the information I've been asked, I've been given, and how am I going to produce the thing I've been asked to produce, is a separate skill of its own, and to not neglect that skill and to think, yeah, I've got a really good understanding, philosophically and conceptually of what's going on here, and that's a good thing, and you shouldn't neglect that, but also not neglecting the focusing on how you make decisions of what to do.
Yeah, roll your sleeves up and.
Yeah, but also, if you have an opportunity to ask the person teaching you, to ask them, how do you decide what to do? Because often my students don't realise that that's what their problem is. They don't realise that they've never actually asked how the decision was made. They've just followed on the example where the decision was already made. And then when they get to an assessment situation, they don't know how to decide. And so that's what my big advice would be.
I think that's really good advice for calculus 2, because that's a place where you have to work on not just what is the problem and I've got the algorithm for that problem. You have to say, well, firstly, what's the problem, and now which of the algorithms that I have is the one to use in this case.
It's the most reasonably applicable one.
And that's something I think that's pretty new to calculus 2, the fact that you can't just identify the problem and then
Because in calculus 1, you pretty much, if you're not sure, you take the derivative and set it to 0, and you're in pretty good shape, right? Yeah.
Something will happen.
Yeah, something good is going to come of that, right?
You've got one big method of differentiation. It's
Yeah.
got several parts to it, but
so
it's
it's
one.
calculus 2 got a lot of integration in it.
Yeah.
Yes.
Yeah, so I always say differentiation always works, right? You can use, there's about 3 or 4 different rules, and it doesn't, as long as they actually apply, it doesn't really matter which one you use. Some are more efficient than others, but I mean, you could rewrite it with a negative power and use the product rule if you in a chain rule if you wanted, or you can use the quotient rule to make it come out the same in the end. But integration is 8 or so techniques, and sometimes none of them work, and sometimes some of them will work, but it will literally take 15 pages, and another one will be 3 lines. So it's much harder to decide with integration what to do, because things don't look the same, as they're not always written in a format where it's obvious to choose.
And not every integral has an analytic.
No.
Antiderivative,
Yeah.
I think a thing that's important to remember is that there's a lot of math that you learned along the way before Calc 2 that may have felt fairly irrelevant along the way. Like there are, for instance, a lot of trig identities that maybe you played with at some point that felt pretty much just like you were jumping through hoops of trying things out in these different ways and really just like practicing like factoring equations but using trig functions and identities, and it felt it's fairly useless, but just coming, which is not actually probably part of what you've done in this Calc 1 course, but kind of remembering that you have a lot of those skills and a lot of those identities and things that you may have done in pre-calc or even your Algebra 2 classes that will be super useful in Calc 2 because you have this fluency, and so to not forget that there's a lot of things from a while ago that might be useful.
And it's always
Those chickens are coming home to roost.
Yeah.
and it's always appropriate to look out for things that seem vaguely familiar.
Exactly,
Ooh, that
exactly.
looks
Like that looks
vaguely
like something.
Pythagoras-y.
Yeah.
Like
Maybe
that
that's sort of
seems like,
useful.
geez, all those things are squared. I think there was something where a bunch of stuff was squared. What was that? Or
Yeah.
just kind of looking for patterns of things that might be something you may have vaguely remembered, and to not berate yourself for not fully remembering what they are. But this skill is much more about remembering that it exists than remembering what it is. Because
Remembering
if you know that
that
it
you once
exists,
knew
you
it.
can go find it.
Yeah.
But if you can't recall that it ever existed, you've got yourself kind of in a pickle.
And a lot of it is based on that. So, ooh, yeah.
Seems
What
like
else-
there
what
ought to
else-
be a thing for this.
What else had a sin x times cosine x?
Right.
Yeah.
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 We talked a little bit about when we were talking about Euler about how just how brilliant he was at those connections. He could draw on everything he knew, and that's why he was able to solve all these integrals that he never been solved before. Anyhow, okay. Well, thank you very much. I really appreciate it.
No problem.
At a conference, these people left rooms full of games and entertaining discussions to come talk calculus. So if you were here, I'd ask you to give them a round of applause.
Yeah.
And also, just so you know, it's 10:15 at night, and we have been participating in things at our conference officially since 9 this morning, but I went to a really excellent breakfast, actually, with John, starting at 7:30 this morning, and I truly, as he says, can't wait to get back downstairs to have more conversations about teaching math. So it is a pretty passionate group of people here.
Well, we wish you all the best.
Yes.
Good luck.